What's up, guys? This is Chris McCormick. In this video, I'm going to be taking us through a tutorial on how to apply BERT to document classification. So if you've been following along with my YouTube videos, then you know we already kind of covered how to fine-tune BERT for sentence classification. And so, aren't sentence classification and document classification kind of the same thing? Yes, pretty much. The main difference here is that BERT has this limitation around the length of the input text that we feed it. So this is going to be about how we address that issue basically. And in order to do that, we're going to need a different data set. So for this notebook, we're going to be using this data set of Wikipedia comments taken from like the edit pages of Wikipedia. They contain some of them contain personal attacks from one user to another. We'll talk more about the data set in a bit here. But as a bonus here, at the end of the notebook, I'm also going to take us through an example of applying BERT to semantic similarity on text. So we're going to use our fine-tuned BERT model to create embedding vectors for all of the comments in this data set. And then we'll be able to do a nearest neighbor search to either compare the comments against each other to find the most similar ones, or we can also like type in our own text, use BERT to vectorize that, and then find the most similar comments to our input text. So that'll be down at the end. If you're new to working with BERT and fine-tuning BERT, then you might want to check out my sentence classification post first. Here we're going to focus more on the changes necessary for applying it to document classification. And then in the other direction, if you've already read through the sentence classification notebook, then a lot of this will be familiar. In particular, sections 1 and 4 are completely unchanged. Section 4 is kind of where we implemented our training loop. All right, so let's get into it. Again, setup's unchanged. We're going to use a GPU, and looks like they gave us a Tesla T4. Cool. And we're going to use the Hugging Face Transformers library. That's going to be our interface to BERT. So I've got to install that. All right, let's talk briefly about the data set itself. So this was created by the Wikimedia group. They were interested in training a machine learning classifier to automatically detect instances of one user personally attacking another user in the comments section of the edit pages. So the data set comes in 2 files here, annotated comments, which contains the comment text, and then the annotations, which contain the labels. And they've actually, they published a paper on this, and they've got a nice example notebook for getting started with this data set. So, I borrowed some of the code from that. It also has kind of a nice baseline implementation of a classifier. And what's cool is when we apply BERT to this, we'll do a lot better than that. So we'll need to download those 2 files. They're available on Figshare. And then we're going to use pandas to parse those TSV files, get the comments and the annotations. Can look at the first few rows of the comments table just to see what's in there. So the comments are all uniquely identified by this revision ID. And we don't care about most of these columns, year, logged in. We will use the split. That tells us whether to use the comment as a training sample or a test sample. Yep, so there's train, test, and development. We can count up those. There's about 70,000 training samples and 23,000 in the test set. The annotations are interesting. So they actually had, I think, something like 10 labelers label every single comment. So that's why you see, all 5 rows here have the same comment number that they're referencing, but different workers. And then the way we actually decide whether a comment contains a personal attack or not is that we group together all of the labels from these 10 different reviewers, and then we select just this attack column. This is kind of the summary. If any of these is 1, then attack will be 1. And as long as more than 50% of the reviewers said that this contains a personal attack, then we'll say, yes, it does contain an attack. So we'll calculate the labels that way, and then we'll add that to the comments table. They also use these kind of special indicators, sentinels for new lines and tabs. So we're going to replace those with just empty white space. We'll apply the training and test splits. And then we can print out, a handful of these comments, specifically the ones that contain attacks. So be prepared. You might either find this appalling or kind of amusing. Pretty awful stuff in here. Anyway, let's scroll past all that. So let's look at the class balance on the data set. If we look at the number of comments that are labeled as attacks compared to the total number of comments, it's about 11%. So it's very imbalanced. And what that means is that, if we were to just predict that for every comment, if for every comment we predicted, no, that does not contain an attack, then we would get 88% accuracy. So we've got to be careful about how we evaluate accuracy on this data set. And we've got a technique in here for addressing that. Okay, so now you know a little bit about the data set. Let's talk about BERT and its input length limitation. So we use the BERT tokenizer to split the text into tokens, and BERT has a maximum input length of 512 tokens. Now, before we worry too much about that limit, let's get a feel for what does 512 tokens actually look like? How much text are we talking about? So we need the BERT tokenizer for this. We've got to use Hugging Face to load that. And the first comment in the data set happens to be longer than 512 tokens, so it's a good one to look at. Doesn't contain an attack either, so it's not as painful on the eyes. So we will grab that comment. We're going to split it with the BERT tokenizer. All right, so this first comment contains 591 word piece tokens. Here is the raw comment text itself. Notice it's got a lot of these quotes in it. So we're going to see those again when we split this into tokens. So that's what 591 tokens looks like. Let's break it into tokens, and then we'll separate out the first 512 tokens to see how much text fits in that limit. And I should have mentioned earlier, I'm using this handy class called wrapper that wraps the text so that it's 80 characters wide. Doesn't go off the end of the screen for us. All right, so this gets a little painful to look at because we've broken it into tokens, and every token is separated by a space. So every time there's one of these little ticks, that's a separate token. But there we go. That's the first 512, and then that's the remaining 79 that won't fit in BERT. It's kind of interesting to see how complete the BERT vocabulary is. There's very few subwords in here. I noticed the word philosophy was broken, but I think that's because it was misspelled. It's missing an O here. All right. Maybe to quantify that a little bit more, let's say if we truncate it, and then let's say if we try to count the words rather than just all the tokens, as well as the number of sentences. So we're going to count the words just by essentially counting the number of white spaces, and then count the sentences by counting essentially the number of periods followed by a space. So this is 330 words, 20 sentences. Okay. So it's a fairly large amount of text that will fit into the BERT input. But it's obviously possible to exceed that. So how do we handle that? Well, a couple key points here. Unfortunately, there's not really some obvious solution to this problem. But we're going to talk about a number of different ideas that you could try. And then, of course, I think looking at the statistics of the data set is helpful, as well as maybe kind of thinking about where you think, in the text might be the most relevant information. So we'll do that for this data set down in section 3.3. And there's actually a paper published that looked at this specifically, how to fine-tune BERT for text classification. So they're looking at handling these larger pieces of text. And they played with the IMDb movie review data set. So they tried a number of things. The simplest one is just to drop some of the tokens, basically, like let go of some of the text and hope that, what's left is enough to perform whatever you're trying to do well. And options for that are, you can drop them from the beginning of the text or just truncate it, cut them off the end. Or you could actually keep some of the beginning and some of the end and then cut out some of the middle. So let's actually go look at their paper to see their findings on this. It's down in section 5.3. There we go. Okay, so they describe these three truncation methods as head only, meaning they keep the beginning of the text. And they're saying, 510 here is because we have to leave space for the special CLS token on the beginning and the SEP token on the end. And keeping just the last tokens as tail only, and then head plus tail is what they called cutting out some of the middle. And apparently, they tried some different numbers here and found that picking the first 128 tokens plus the last 382 worked the best. And so we can see the results up here on the IMDb data set. So these are error scores, so lower is better. And this head plus tail approach is actually what performed best for them. And it even outperformed some of these more clever approaches down here, these hierarchical ones, which we'll talk about now. All right, so another strategy you could take is to break the text into multiple chunks, process the chunks separately, and then somehow combine the results. So what this would look like, let's say you have a piece of text that's 1,200 tokens long. So you'll break it into two chunks of 512 tokens each, and then one more for the balance, whatever that is, like 176. So in the paper, the way they handled that is they divide the text into chunks. Then for each of those chunks, they'd send it through the BERT model and extract an embedding for the chunk. And then they would pool together the embeddings, which just means, combine them in some way. And they tried min pool or max pooling, averaging, and then also self-attention layer. And, as clever as those ideas sound, none of them actually outperformed the simple head plus tail method. So there's also a discussion about this topic in a issue thread in the GitHub repo for BERT, the official repo. You can take a look at that. So they're asking about, the same problem, document classification. And this user is suggesting something a little bit different than the paper. They're doing the chunking again, but they're suggesting that you actually run all the way through to the final classification and then average together the classification scores. So a little bit different because it means you're pooling the results after the final activation function of the classifier. And let's see, yeah, and then I wanted to thank Mariano Comp. I had some discussion with him in the comments on the sentence classification videos. He helped me kind of think a little more practically about some of the concerns here. And a suggestion that he had was to maybe try text summarization. And someone else mentioned that in here as well. Yeah, summarizing the document. So the idea is that you would figure out a way to condense the document into a smaller length that BERT can handle. And I won't go into that in too much detail because I haven't actually done text summarization before. I can tell you that there's two types. There's extractive and abstractive text summarization. Extractive means that you go through the document and you pick out what you think are the most pertinent sentences, and then you return those as the summarization. So you don't modify the text, you just kind of pick out the most pertinent text. Abstractive, you're actually allowed to generate new text to try and summarize. So, whether one would work better than the other, I'm not sure. I think it is worth noting that, as part of extractive, you typically get to pick the number of sentences that you want to summarize the document down to. So you do kind of have the ability to pick, since 512 tokens is kind of a lot, you might be able to keep a lot of text actually in the summarization strategy. So that's another idea to pursue if you think it'd be interesting. Let's take a look at this Wikipedia Commons dataset though, because I think that can help kind of, enlighten our thinking on the topic. So to do that, we're going to tokenize now all of the comments in the data set. We'll use the encode function to do that. The encode function converts splits the sentence into tokens, adds the CLS and SEP tokens for us, and maps them to their IDs. So we'll do that. And a consequence here is that every time it comes across a sentence that's longer than BERT's maximum input length, it throws an error. Or throws a warning rather. So we've got this huge output window of warnings on the sentences. We'll just disregard that though. And and then as part of training, we need to extract the labels from the data frame. So we take the attack column and we're going to convert it from Boolean values to integers, either 0 or 1. And then real quick, we'll just print out the statistics again. So 8,000 positive, 61,000 negative. Okay, but back to the comment length. So when we did the conversion up here, we created this list. Yeah, let's go look at it real quick. Scroll up there. There we go, lengths. So every time we encoded a sentence, we stored its length in this lengths list. So back down here, we can use that data to print out the minimum sentence length and maximum length and median length. So there's some really long comments in there. Interesting. But the median length is fairly short, well within our 512 length, 512 token limit. So let's also plot the distribution to get a feel for how the lengths are distributed. In order to do that, to keep the x-axis reasonable, I had to cut out all of the really long comments. So any of the length values that are greater than 512, we're going to truncate to 512. And then we'll use a distribution plot here. We can take a look. Yeah, so number of comments, comment length. So we can see that the majority of these comments are less than 100 tokens long. Over here is all the comments that were greater than 512. Let's see how just how many of those there were. It looks like 1,600 of those 70,000 sentences were longer than 512, and that's only a little over 2% of the data set. And then something interesting here that we can look at is, how, like of these sentences that are super long, how many of them were positive samples, ones where there is a personal attack? And it turns out that none of them are, which, I think kind of makes sense if you think about it. If you've got this long, well thought out, well-reasoned comment, it's probably something constructive rather than a personal attack. When we looked at the personal attacks, a lot of them are just, like barfing garbage. So they're not as long. Anyway, so given this distribution, and given the fact that the comments that we're trying to find, the ones that contain these personal attacks, tend to be short, I think we can safely just truncate these things. And so we could truncate to 512. I actually went further and truncated to a length of 128. And I did that because the sentence length, this maximum sentence length, does impact the performance of the model in terms of how long it takes to fine-tune it and how long it takes to run it to extract embeddings. So 128 seems like a good number where, it's close to the elbow of the distribution. It's a power of 2, which we're always drawn to. So we're going to truncate them all just down to 128. And what we'll see here is that that actually works pretty well. Okay, so now that we've addressed this length problem, all that really is left is for us to train the model on this data set and then test it on the test set and see how our performance stacks up. So I won't be going through the training and test sections in as much detail since I already covered those in the previous tutorial on sentence classification. So again, if you want more detail on those pieces, then definitely check that other tutorial out. I'll put the link in the description. Yeah, so I haven't touched the rest of the training code, and we just need to do a little final data prep here. We need to create the attention masks. These tell the model the difference between the actual tokens versus the padding tokens that we added to the end. And we will take a 90-10 split of our training data to use 90% for training and 10% as a validation set. And this is separate from our test set. The validation set we'll test our model against it after the end of each training epoch. So it's just kind of to tell us like how we're doing as we, how the model's doing as we train it. We need to cast our data to PyTorch tensors, and we'll use these data loader classes to feed the data to the model in batches of 32 samples at a time. And then to actually do the fine-tuning, we'll use this BERT for sequence classification class that comes from the PyTorch Hugging Face transformers library. And we use 2 labels here for binary classification. If you were to set this to 1, then what the Hugging Face library does is it interprets that as you wanting to build a regression model rather than a classification model. So seems kind of redundant, but yeah, we use 2 labels here instead of 1. All right. Have to create the optimizer and the learning rate scheduler. And then we have our big training loop with some helper functions here defined first. We'll set the random seeds. And the training consists of, going over 4 epochs, training over the full training set. Here's all the gradient calculations, the forward pass, the backward pass, and then updating the weights and updating the learning rate. And then once all of the training samples have been fed to the model, then we do this validation. All right, so here's what the output looks like. It does take a while to run. Yeah, we can plot, once it's done, we plot the training loss, make sure that it's learning. All right, and finally we can test it against the test set. So to do that, we need to kind of do the same data preparation that we did for the training data. It's a little more consolidated in this cell, just since we already kind of talked through all these different pieces. But we'll go through all the test comments, we'll encode them into the word IDs. Yep, do the padding, attention masks, convert to tensors, create the data loader. And then we can run the model against all of these test samples. Yep. Goes pretty quick, takes about 3 minutes. Okay, now we can look at the actual results. So since we process these in batches, we have to combine those batches into single matrices of predictions, and then we're also kind of assembling here the list of true labels. We can take a look at the first 10 predictions, and what we can see is that the first column is for label 0, and the second column is for label 1. So what this is saying is that the model is outputting a high confidence that this training sample or test sample, excuse me, is not a personal attack, and then the classifier for personal attacks agrees. It says, the confidence is very low that it's a personal attack. And, so it's the same for the first 10 test samples. And if we look at the true labels, then, they're all 0. So this is correct. All these predictions are correct. The results are looking pretty good so far. So the next thing to do is to measure our performance on the entire test set. The performance metric that the authors of this dataset chose is the ROC-AUC, area under the curve. And this is a pretty popular metric, so you should be able to find some good tutorials out there on it. Real quick though, I'll try to give you the most important intuition about what this metric is trying to measure. Let's say as an example that you have a website and you actually want to deploy this classifier to identify personal attacks in the comments section. So in order to do that, you're going to have to pick a threshold. You're going to have to decide how confident do you need the model to be in its classification in order for you to flag a comment as a personal attack. So if you are, maybe looking for something more hands-off, where it'll get, hopefully most of the comments, not all of them, and you don't want to review that many comments, then you might set kind of a high confidence threshold, because that will minimize the number of false positives that the classifier produces. And, kind of at the cost of like potentially missing some of the personal attack comments. On the other hand, or on the other end of it, you might have it might be really important to you that all of these personal attack comments are identified and removed. Maybe it's really important to your brand in some way. So if that's the case, then what you're probably more likely to do is set a lower confidence threshold, and then have maybe like a human moderator kind of review the results and leave it to them to separate the actual attacks from the false positives. So in that scenario, you end up with more false positives, but fewer false negatives. So there's kind of a trade-off there, and you can put this threshold in different places. So how do you create a score for the model? So the ROC-AUC measures the performance of the model at a number of different thresholds. And so it reflects the model's ability to do a good job, whether the threshold is high or low. All right. So we'll take that metric from the scikit-learn package. We're using the, and we saw this up here, we're using the logits, which are the outputs of the classifier before going into the final activation function. If it had gone through the activation function, then these would be values between 0 and 1, or -1 and +1, something like that. But we're just doing the value right before that. And here's the score we get. We get 0.969, and that's actually a really good score. So the original notebook provides this baseline implementation where they use TF-IDF and apply logistic regression, and they get 0.957. I've also tried a little more advanced approach to this benchmark, where I trained a word-to-vec model on the data set, and then I used that as the embeddings for an LSTM. And that approach got me up to 0.966. So just by kind of throwing BERT at this problem, we've got a better score than either of those. So that's pretty cool. Okay. So now that we've trained this model, it's a good idea to save it to disk and back it up so that we don't lose it. So this code will just write the model to disk in this model save folder. And then to actually back it up, you can either download it to your local drive, or you can copy it to your Google Drive using these two cells here. So that about covers it for the document classification portion of this notebook. Before we move on to the semantic similarity stuff, though, I wanted to make a quick plug for this notebook. If you want a copy of it, I've made it available to purchase, for purchase on my website. So real quick, I want to show you what you'll get with that. There's two parts to it. There's the tutorial that you're watching now, plus the notebook. And then I've also included my research notes and any questions I've been asked on this topic. So for my research notes, whenever I find a blog post or a forum discussion or a paper that's relevant to this topic, I add it there in this notebook and any notes that I have on it. And then every time I like to keep an organized collection of questions that have been asked. So that is in this notebook as well. So I hope you guys find it really valuable and appreciate your support. Okay, on to semantic similarity. So semantic similarity, if you're measuring that between two pieces of text, then what you're doing is trying to assess how similar in meaning they are. And the way we do that is by creating feature vector representations for the text in our data set. So for each comment, we need to produce a embedding or a feature vector that represents it. And then we can compare text by using a distance metric like the Euclidean distance or cosine similarity to compare those vectors, and the result can be taken as a measure of how similar in meaning the text is. So I actually am working on a separate notebook that will go into a lot more detail in this subject, but there's a specific reason that I chose to include a little section on it here in this notebook. The reason for that is that the CLS token on the final layer of the BERT model, if you don't fine-tune BERT at all, then it's not considered to be a good sentence embedding. So here is Jacob Devlin, the author of BERT, expressing that. So there's not any sentence embedding in BERT. The hidden state of the first token is CLS token, is not a good sentence representation. If you want sentence representation that you don't want to train, so that's kind of the key point there, is that if you were to train the model, then you might be able to produce a better sentence embedding. So we've fine-tuned a BERT model on this comments data set. And I suspect that because we've done that, because we've built this classification model, the embedding representing the CLS token here at the final layer is now a much better vector to use to represent the comment. And the reason that it's not good prior to fine-tuning is that the BERT model was trained, if you remember, on next sentence prediction and predicting masked words. So for those two tasks, the CLS token isn't necessarily motivated to capture the meaning of the sentence. All right, so to do this, we need to make sure that the model is outputting the hidden states so that we can use that for sentence embeddings. The way I've done that is I've actually reloaded the model and set that flag to true. You can go and edit the flag, but I'm not sure if that actually achieves what we want. So here's how you load a BERT model from disk. Remember, we saved it earlier to this model save directory. So we'll load it from that directory. And this time when we load it, we're going to set this output hidden states flag to true. We'll also load the tokenizer from disk, even though it's not strictly necessary. We haven't changed the tokenizer at all. And then we'll copy the model to the GPU again so we can run it. All right, so in order to do this, what we need is a function that will allow us to take a BERT model and a tokenizer and an input string, and then return to us a feature vector representation. So this will look pretty similar to what we've done already. We'll encode the text, we'll truncate it, we'll add the CLS and SEP tokens, we'll pad it out, and then define the attention masks. convert to tensors, put the model in evaluation mode, copy this stuff to the GPU, and then run the text through the model. And because we haven't provided labels in this call, the model knows that we want to do like a forward pass and return the logits that we were using for testing, but now also the encoded layers. That's the hidden states that we wanted it to return. And we're going to use that CLS token from the final layer. So we'll set the indices here and retrieve that from the hidden states. So now that we've got that function defined, we can try applying it to one of the comments in the data set. Just picked comment 10. And in this section, you'll see me use this text wrap functionality. It'll help print these comments in 80 character width columns. So we'll take that comment, feed it to our text to embedding function, and then we get our vector. So it's working. All right, so now what we need to do then is to apply that function to every comment in our data set so that it becomes searchable. So we'll loop over all of the comments, and this takes a while. This took about an hour for me to run. Part of the reason for that is that the text to embedding function is only converting one piece of text at a time. If you were to batch those inputs, you'd get better efficiency out of the GPU. So, and that would speed up this overall time. But we'll do it for all 115,000 comments. It took about 55 minutes. And then what we end up with is this big matrix of 150,000 or 115,000 word comment embeddings, each with 768 features. And since that took so long, we want to save that to disk. So we'll write it out to that same model save folder using NumPy, and then we'll back it up to Google Drive. All right. So now we've got this function to vectorize text, and we vectorized the whole comment data set. Now we can do the similarity search. And by search, I mean that we're going to be able to take a input text and compare it to all the comments in the data set and find the most similar ones. So that search is called k-nearest neighbor search. K is the number of results that you want returned. And so we need a library that's going to implement KNN for us. You can find that in scikit-learn. One that I have some experience with and am kind of partial to is the Facebook AI Similarity Search Library. They have a really nice GPU implementation. And in fact, they have a lot of these KNN libraries are designed with approximation techniques. And the Facebook library has that as well. They also, though, happen to have a very efficient brute force implementation of KNN on the GPU. So that's pretty nice because it means you don't have to build an index for the approximation technique, and you don't have to compromise at all on the accuracy of your results. So we'll be using FACE in this notebook. I think in the other notebook, I'll probably show some other options. So we need to install that. And then here's the code for setting up our FACE index that allows us to perform the KNN search. So the way that's done is we first create a CPU index, and I'm using the Euclidean distance here. You could also try cosine. Flat just refers to the fact that this is a brute force search. It's not an approximation technique. We're going to use one GPU here. FACE does actually support multiple GPUs. If you did have multiple GPUs, what's cool is you can actually shard the data set and split it across the GPUs to kind of speed up your search. All right, and then we kind of the process with FACE is that you define the CPU index and then you copy it to the GPUs. So we do that, and then we add our vectors to the index. Again, it's not really an index because we're not doing any approximation, but great. So now that we've got our index set up, it's ready to search. And as the first example here, we'll take one of the comments from the data set, and we'll use that as our query text. So we'll pick comment number 4, and we'll use face here to find the k equals 5 most similar comments in terms of meaning. So that returns the distances and the indices of the results. So we'll iterate over those indices, we'll look it up, and we'll retrieve the text from the original comments data frame and print out that comment number plus the distance and then the text itself. So the input comment here, comment number 4, says this page will need disambiguation. And when we search the data set, the top 5 results we get are comment number 4, we get back itself with a distance of 0, so that's good, that makes sense. And then the next result, this page needs to be expand. So that seems like a pretty good sentence that's close in meaning. Yeah, so yeah, the results here are all kind of like about general sort of like the page needing to be improved in some way. And then with that text to embedding function that we defined, we can also define our own arbitrary text. We don't just have, we're not limited to just using, comments from the data set. So what I did here is I took comment number 4, which said this page will need disambiguation, and I kind of paraphrased it. I rewrote it using different language, turned it into the meaning of this page needs to be clarified. So we can create an embedding for that piece of text and do the search in the same way. And what we get back, top result is comment number 4. That's great. So BERT seems to agree that I translated this comment pretty well. Yeah, please add in more information on this topic. It seems good. All right, and then just another one that I tried out. You can try out your own sentences. I tried, this article really needs more citations. That's a pretty common comment. So I intend to expand the article. I, of all people, shouldn't be saying this, but the article needs citations. Please expand if possible. Yeah. So there you go. That's kind of a quick tour on semantic similarity, but I will go into more detail in that future notebook. All right, thank you guys. It's been fun.